What if the coldest thing in the universe isn't space itself? Today, we're uncovering the terrifying truth about cosmic cold, the hidden reality of heat in the universe, and why warmth may be far rarer than we ever imagined. And by the end, you may realize that every warm sunrise on Earth is rarer than you ever thought possible. Now, let's begin. If an astronaut were exposed to open space without a suit, they would not freeze to death. Not immediately. Not even close. On the sunlit side, skin surface temperature would climb past 240 degrees Fahrenheit, hot enough to cause third-degree burns within seconds. The unfiltered solar radiation pouring in at roughly 1,360 watts per square meter would cook exposed tissue before the body ever had a chance to lose meaningful heat. The astronaut would not turn into a human popsicle. They would blister. That is not what science fiction told you. That is not what decades of space movies have been selling. And that gap between the story and the physics is exactly where this conversation begins. Almost everyone carries the same mental image of space, a vast, frozen wasteland, brutally cold, hungry for heat, waiting to drain the warmth out of anything that enters it. It feels obvious. Space is dark. Space is empty. Of course, it is cold. The assumption is so deeply wired into the culture that questioning it feels almost absurd. But the assumption is wrong. Not slightly wrong, not technically wrong in some obscure academic sense, fundamentally structurally wrong in a way that once you understand it, you cannot unsee it. Here is what actually happens when you expose an unprotected human body to the vacuum of space. On the sunlit side, radiation from the sun hits the skin with enormous intensity. There is no atmosphere to filter it, scatter it, or soften it. The energy arrives full force, and the body absorbs it. Temperature on that sunlit surface rockets upward. Meanwhile, on the shadowed side of the same body, thermal radiation bleeds away into the void, with nothing coming back. That side plunges toward extreme cold. The same person at the same moment simultaneously burning on one side and freezing on the other, separated by the width of their own torso. That is not cold. That is something far stranger. That is the absence of moderation. Now consider this. The International Space Station, which orbits Earth at roughly 250 miles above the surface, in what most people would call the frozen void of space, runs on enormous radiator arrays, specifically designed to dump heat. Not to generate heat, to get rid of it. The station's electrical systems, its computers, its scientific equipment, the metabolic output of 6 human bodies, all of it produces heat that has nowhere to go in the vacuum. Without those radiators, the interior temperature would climb until the electronics failed and survival became impossible. Thousands of satellites in Earth orbit carry thermal control systems engineered to prevent overheating. NASA and every other space agency spend extraordinary resources, billions of dollars across decades of engineering solving the problem of excess heat in space, not the problem of too much cold. Let that sit for a moment. The agency most associated with venturing into the frozen void has spent more engineering effort keeping its machines from overheating than from freezing. The reason for this apparent contradiction cuts to the core of what temperature actually is, and why the concept behaves so strangely once you remove the one thing that makes it feel intuitive on Earth: matter. Specifically, lots of it. Moving, colliding, transferring energy through contact at scales so dense and so constant that humans evolved to experience temperature as an ambient property of the surrounding environment, rather than what it actually is, a description of particle motion. Space is not cold the way a walk-in freezer is cold. A freezer is full of cold air, cold molecules pressing against everything inside, extracting heat through direct physical contact. Space has almost no molecules at all. The vacuum between stars is not filled with cold stuff. It is filled with almost nothing, and nothing cannot steal your heat through contact. Nothing cannot drain your warmth the way wind does on a January night in Minnesota. Nothing is not cold. Nothing is nothing. The terrifying truth about space is not that it is brutally cold. It is that it is something the human nervous system has no evolved framework to process an environment where the familiar rules of thermal experience simply do not apply, where the same laws of physics that govern a warm summer afternoon operate under conditions so alien that every intuition you have built up through a lifetime of physical experience becomes actively misleading. This is the question worth taking seriously. What is temperature really? When you strip away everything familiar, the air, the surfaces, the wind, the shade, what remains? The answer to that question changes how you understand not just space, but the nature of heat itself, the origin of the universe's faintest glow, and ultimately, what it means that any warm place exists at all in a cosmos that seems almost philosophically committed to being cold. That investigation starts with the most basic question of all. If space is not cold in the way we experience cold, then what is temperature really? And why does the concept itself break apart the moment you step beyond Earth's atmosphere? Grab a metal spoon and a wooden spatula out of a kitchen drawer. Leave them both sitting on the counter overnight. Come back in the morning. Touch them both. The spoon feels cold. The spatula feels neutral, maybe slightly warm. They have been in the same room at the same ambient temperature for the same number of hours. They are, by any thermometer measurement, the same temperature. But they do not feel that way. And that gap between measurement and sensation is exactly where the physics of space begins. Temperature is not a sensation. It is not a property of how something feels against your skin. Temperature is a measurement of how fast particles are moving. In any substance, gas, liquid, solid, the atoms and molecules are in constant motion, vibrating, bouncing, colliding. Temperature is the statistical average of the kinetic energy of all those particles. Higher temperature means faster average motion. Lower temperature means slower. That is it. That is the entire definition. When you touch the metal spoon, it feels cold, not because it is colder than the wood, but because metal conducts heat away from your skin far more efficiently than wood does. Metal has high thermal conductivity. Its tightly packed atomic structure transfers vibrational energy rapidly from your warmer hand into the cooler bulk of the spoon. Wood is a poor conductor. The energy transfer is slow, sluggish, barely noticeable. Your nervous system interprets the rate of heat loss as temperature. Fast loss reads as cold. Slow loss reads as warm or neutral. The thermometer disagrees with your hand, and the thermometer is correct. This distinction between the rate of heat transfer and actual temperature is not a minor technicality. It is the foundation of why everything about space feels backward. On Earth, temperature feels like a property of the environment, because the environment is saturated with matter. Step outside into cold air, and billions upon billions of nitrogen and oxygen molecules collide with your skin every second. Each collision transfers a tiny amount of energy away from your body. Collectively, those collisions add up to a continuous, relentless extraction of heat. The cold air is cold because it is full of slow-moving molecules that absorb your faster-moving thermal energy through direct contact. The cold reaches you because something is there to carry it. 1 cubic centimeter of air at sea level, roughly the volume of a sugar cube, contains approximately 25 billion molecules. Write that out, 25 followed by 18 zeros. That inconceivable swarm of particles is what you breathe in with every breath, what brushes against your skin with every movement, what conducts cold or warmth to your body through sheer force of molecular numbers. Now go to interstellar space. That same cubic centimeter in the void between stars contains on average about 1 atom, sometimes less. The density is so extraordinarily low that the word gas barely applies. You could not measure the temperature of that region with any conventional thermometer because there is simply not enough matter present to transfer any detectable energy to the instrument. A thermometer in deep space does not read the temperature of the space around it. It reads its own temperature, whatever equilibrium it has reached, based on what radiation it is absorbing and what it is emitting. The instrument becomes the measurement. It is telling you about itself, not about the void. This is the first fracture in the common understanding. And to see why it goes even deeper, you need to understand the three mechanisms through which heat moves from one place to another, because only one of them works in space, and understanding that changes the entire picture. The first is conduction. Physical contact between two objects transfers thermal energy from the hotter to the cooler through direct molecular interaction. Press your palm against a cold granite countertop, and heat flows out of your hand into the stone through the contact point. This requires matter. It requires touch. In the vacuum of space where there is nothing to touch and nothing touching you, conduction is entirely irrelevant. It contributes exactly zero to the thermal experience of any object floating in the void. The second is convection. Heat moves through the circulation of fluids, liquids, or gases that carry thermal energy from one region to another as they move. This is what drives weather. Warm air rises, cool air sinks, wind carries thermal energy from the equator toward the poles. A fan cools you on a hot day, not by lowering the air temperature, but by moving it, replacing the warm layer of air near your skin with cooler air from farther away, accelerating the convective heat loss. Convection requires a fluid medium. In space, there is no fluid. There is no circulation. The vacuum is still and empty in a way that no location on Earth can approximate. Convection, like conduction, simply does not exist as a thermal mechanism in the void. The third mechanism is radiation. Every object with a temperature above absolute zero, which means every object in the known universe, emits electromagnetic radiation continuously. Your body is emitting infrared radiation right now invisibly in every direction without stopping. The walls of the room around you are emitting it back. The sun emits it across the full electromagnetic spectrum, from radio waves to gamma rays. This radiation carries energy through empty space without requiring any medium whatsoever. It crosses vacuum as easily as it crosses air. It travels at the speed of light, and nothing about traveling through, nothing slows it down or diminishes it until it strikes something and transfers its energy. Radiation is the only mechanism of heat transfer that functions in vacuum. This single fact restructures everything. It means that in space, your thermal experience is determined entirely by what radiation sources are shining on you and what your own body is emitting outward. The surrounding vacuum contributes nothing. It neither warms nor cools. It is thermally inert, not because it is cold, but because there is so little of it that it barely participates in the physics at all. This is where the physics becomes genuinely strange. Vacuum is not cold. Vacuum is not anything. It is the absence of the medium through which the concepts of hot and cold normally operate. Calling space cold is like calling silence loud. The statement does not quite make contact with reality. Cold, as humans experience it, is a description of energy loss through matter. Where there is no matter, there is no cold in that sense. There is only radiation, what you receive and what you emit. And yet, there is a temperature to space. A real one, measurable, precise, meaningful. Not the temperature of vacuum itself, but the temperature of any object that has been left alone in that vacuum, long enough to reach equilibrium with the only thing the void does, contain the faintest possible glow of radiation so ancient and so dim that it took humanity's most sensitive instruments to detect it. If space is not cold in the way we experience cold, then what temperature is actually being measured out there, and where did it come from? Every object in the universe above absolute zero radiates, no exceptions. A rock, a human body, a spacecraft, hull, a grain of interstellar dust, anything with thermal energy continuously emits electromagnetic radiation, leaking photons outward in every direction, at every moment, without pause. The colder the object, the longer the wavelength of that emission. Human bodies radiate in the infrared. The sun radiates across a broad spectrum, peaking in visible light. Objects near absolute zero radiate in microwaves. But all of them radiate. It is not a choice. It is physics. In vacuum, this is the only game in town. Conduction needs contact. Convection needs fluid. Radiation needs nothing. It crosses empty space at the speed of light, transferring energy without a medium, without friction, without loss. Strip away the atmosphere, remove every molecule of gas, and radiation becomes the sole authority over thermal experience. Everything else steps aside. The consequences of this are more extreme than most people realize. On the exterior of the International Space Station, two surfaces separated by a few centimeters of metal can exist at temperatures more than 200 degrees Celsius apart, not across the station, not between the sun-facing side and the shadow side of the entire structure, across the thickness of a single panel. The surface directly exposed to solar radiation sits at around positive 120 degrees Celsius, hot enough to boil water, hot enough to cause severe burns on contact. The surface facing away from the sun, radiating its heat into the void with nothing incoming to replace it, drops to around negative 100 degrees Celsius. Same piece of hardware, same moment in time. Opposite sides of a structure thinner than a textbook. On Earth, that temperature difference would be physically impossible to maintain across such a small distance. Air would immediately conduct heat from the hot side toward the cold side. Convection currents would form and redistribute the energy within seconds. The gap would collapse toward an average, almost before it had a chance to develop. The atmosphere acts as a thermal moderator, so automatic, so constant, that living inside one makes it almost impossible to intuit what heat behaves like without it. The moon demonstrates this with brutal clarity. The lunar surface has no atmosphere, not a thin one, not a sparse one, none. No molecule of gas stands between the regolith and the vacuum above it. When sunlight hits the equatorial surface during the 2-week-long lunar day, the ground heats to approximately 127 degrees Celsius, hotter than boiling water, hotter than a conventional oven set to its maximum. The rock and dust absorb solar radiation with nothing to limit the accumulation. Then the sun sets. Lunar night begins, lasting another 2 weeks. And because there is no atmosphere to retain heat, no blanket of gas molecules to slow the emission of infrared radiation back into space, the surface temperature plummets, all the way down to approximately negative 173 degrees Celsius. That is a swing of roughly 300 degrees Celsius across a single location on a single planetary body, driven entirely by whether sunlight is present or not. Earth's most extreme desert environments, the Sahara, the Atacama Death Valley, experience day-to-night temperature swings of maybe 30 to 40 degrees Celsius. The most brutal continental interiors might push towards 60. The moon swings 300. The difference is not geological. It is not positional. It is atmospheric. Earth has one. The moon does not. The atmosphere performs a thermal service so profound and so invisible that its absence transforms a world from potentially habitable to a landscape of killing extremes within a single rotation. It absorbs and re-emits infrared radiation, trapping heat near the surface. It circulates through convection, carrying warmth from the equatorial regions toward the poles and distributing solar energy across the night side. It buffers, it blends, it smooths every edge. Remove it, and the physics becomes savage. There are no gradients in shadow on an airless world, no gentle cooling as you walk from sunlight into shade. The transition is instantaneous and total radiation present, then radiation absent with nothing in between to soften the step. A rock in sunlight on the moon's surface and a rock 1 meter away in shadow exist in thermal environments, separated by over 100 degrees, with no transition zone connecting them. The International Space Station manages this by engineering. Multi-layer insulation wraps components that must be kept at moderate temperatures. Reflective coatings deflect solar radiation from surfaces that would otherwise overheat. Heaters keep batteries and fuel lines above minimum operating temperatures when they pass into Earth's shadow during the station's 90-minute orbit. The radiator arrays, spanning roughly 2,500 square feet of surface area, face away from the sun and dump excess heat into space as infrared radiation because that is the only exhaust available. The entire thermal control system exists to compensate artificially for the moderating work that Earth's atmosphere does for free. If you think a Chicago winter is brutal, and it is by any reasonable human standard, try living on the moon. You would spend 2 weeks slowly cooking under unfiltered sunlight, then 2 weeks radiating your heat into a void with no insulation between you and absolute cold. You would not freeze or burn on alternating days. You would do both simultaneously, depending on which direction you happen to be facing. That is what radiation dominance looks like, without an atmosphere to intervene. That is what the thermal universe actually is, beneath the comfortable illusion that Earth's air creates. If radiation is the only mechanism of heat transfer in space, then any object drifting deep in the void, far from every star, will cool and cool until it reaches some final equilibrium temperature. What is that temperature and what sets it? Take any object, a spacecraft, a rogue asteroid, a block of iron the size of a house, and place it in the deepest, most isolated region of intergalactic space you can imagine. No stars nearby, no galaxies within tens of millions of light years, no radiation sources of any significance within any direction worth pointing an instrument toward. Leave it there. Wait. It radiates. Slowly, continuously, it sheds thermal energy as infrared photons streaming outward in every direction. Its temperature falls. Days pass, then years, then millennia. It keeps cooling. The temperature drops below the freezing point of water, below the sublimation point of carbon dioxide, below the boiling point of liquid nitrogen, still cooling. Decades become centuries, become geological ages. And eventually, not quickly, but inevitably, the cooling slows. Then it stops. Not because the object ran out of energy to emit, not because the void warmed up to meet it. It stops because the object has reached equilibrium with the only radiation field that permeates every cubic centimeter of observable space in every direction at every moment without exception. The faintest, most ancient electromagnetic signal in the universe, the one that fills the void not with nothing, but with something so close to nothing that it took humanity over 4 decades after the invention of radio telescopes to stumble across it. That equilibrium temperature is 2.7 Kelvin. Any isolated object in deep space given enough time and no other energy input will settle at 2.7 Kelvin, not lower. The incoming radiation from the cosmic background matches the outgoing radiation from the object at that temperature, and the system stabilizes. This is not an approximation. It is not an average with wide error bars. It has been measured to extraordinary precision, 2.725 Kelvin, confirmed by satellite instruments operating above Earth's atmosphere with sensitivity that borders on the absurd. To understand how cold this is, consider the cryogenic benchmarks that physicists and engineers use as reference points. Liquid nitrogen, the substance that flash freezes biological samples and shatters roses in science demonstrations, boils at 77 Kelvin. That is already cold enough to cause severe frostbite on skin contact within seconds, cold enough to make rubber brittle and steel unpredictable. The cosmic background temperature is roughly 28 times colder than liquid nitrogen. Liquid helium, the coldest commonly used cryogenic fluid in laboratory settings, boils at 4.2 Kelvin. Maintaining a liquid helium system requires specialized insulated dewars, precisely engineered pressure controls, and continuous resupply. The infrastructure costs millions of dollars, and the operating costs are substantial enough that many research institutions weigh helium-cooled experiments against budget limitations, the same way they weigh staffing. The cosmic background temperature is colder than liquid helium. Not by a dramatic margin, 2.725 versus 4.2, but genuinely, measurably colder. The universe's ambient temperature is something that cannot be casually reproduced in a laboratory on any budget. Now consider the coldest temperature ever recorded in nature anywhere on Earth. On July 21, 1983, a Soviet research station called Vostok in Antarctica measured an air temperature of negative 89.2 degrees Celsius. That translates to approximately 184 Kelvin. It was a record that stood for 3 decades, a temperature so extreme that exposed skin freezes in under a minute. Diesel fuel gels. And the act of breathing requires deliberate care to avoid damaging lung tissue. By any human standard, it represents the absolute outer limit of terrestrial cold. The cosmic microwave background is nearly 68 times colder than that Antarctic record. The coldest moment in recorded human history on the coldest inhabited continent on Earth is relative to the thermal baseline of the universe, practically tropical. It is closer to the boiling point of water than it is to the temperature of the void between galaxies. That comparison does not just reframe Earth's extremes, it dissolves them. Whatever cold means in the context of human experience becomes essentially irrelevant as a unit of measurement against the cosmos. What makes 2.7 Kelvin genuinely unsettling is not the number itself, it is what the number represents. It is not a local condition. It is not the temperature of one region of space or one era of cosmic history. It is the floor, the universal minimum that the laws of physics impose on any passive object anywhere in the observable universe. No natural process can cool something below this threshold, because the radiation field that sets it is inescapable. It bathes everything. You cannot hide from it, shield against it, or find a region of space where it does not reach. It is the thermal baseline of existence itself. There is something almost philosophical about that. 2.7 Kelvin is not just cold. It is the coldest the universe will allow anything to be under natural conditions right now. It is the temperature of the void, when the void has done everything it can to drain an object of thermal energy and nothing else remains. It is what the universe settles for when nothing interesting is happening. And that, strangely, is what makes it so important. Not as a curiosity, not as an extreme data point, but as a clue, a number that should not exist by accident, that carries information about the most violent event in cosmic history, encoded into its precise value, that has been cooling for nearly 14 billion years from temperatures that would have vaporized anything we can imagine. 2.7 Kelvin is not a coincidence. It is the thermal remnant of the largest heat catastrophe in the history of the universe. And that story begins 13.8 billion years ago. The sun's surface burns at approximately 5,500 degrees Celsius. That number is already beyond anything in ordinary human experience, hot enough to vaporize iron, hot enough to reduce any known material to plasma before it even gets close. It feels like a reasonable upper bound for hot. It is not. 13.8 billion years ago, the temperature of the universe exceeded 10 to the power of 32 degrees. That is a 1. Followed by 32 zeros. The surface of the sun, by comparison, is a rounding error. The core of the most massive star ever observed is a rounding error. Every source of heat that has ever existed in the modern universe combined does not approach what the cosmos contained in its first fraction of a second. The Big Bang was not a hot event. It was the definition of hot, the ceiling of thermal violence that physics as currently understood can even describe. And all of it, every particle, every photon, every unit of energy that would eventually become 400 billion stars in the Milky Way alone, plus the 2 trillion other galaxies in the observable universe, plus every planet, every ocean, every living cell that has ever existed was compressed into a volume smaller than a single atomic nucleus. Before proceeding, one misconception needs to be cleared away completely, because it corrupts almost every intuitive picture people form of what happened next. The Big Bang was not an explosion that occurred inside space. It was not a fireball expanding outward through a pre-existing void the way a bomb expands through air. There was no pre-existing void. There was no surrounding emptiness waiting to be filled. Space itself did not exist before the Big Bang. Space came into being with it. And it was space itself that expanded, carrying matter and energy with it stretching in every direction simultaneously with no center and no edge. Every point in the universe was the origin. There was no outside. This matters for understanding the cooling that followed. The expansion of space is not like gas expanding into a vacuum. It is the vacuum expanding. And as it expands, the radiation within it stretches. Longer wavelengths, lower energy, lower temperature. The universe did not cool because heat leaked somewhere. It cooled because the container grew, and growing containers dilute their contents. In the first second, temperatures dropped from incomprehensible extremes down to roughly 10 billion degrees, still hotter than the core of any star in the modern universe. Still a seething plasma of protons, neutrons, electrons, photons, and neutrinos colliding constantly, exchanging energy, existing in a state of equilibrium so thorough that structure of any kind was impossible. Then came the first 3 minutes. As the temperature fell below roughly 1 billion degrees, something remarkable became possible for the first time: nuclear fusion. Not stellar fusion sustained by gravitational pressure over billions of years. Primordial fusion, brief, furious, and decisive. Protons and neutrons began sticking together. Deuterium nuclei formed. Helium nuclei assembled from pairs of protons and neutrons. Tiny amounts of lithium emerged from slightly more complex reactions. The universe had become briefly a thermonuclear reactor operating at cosmic scale. That window lasted roughly 3 minutes. By the time the universe was about 20 minutes old, the temperature had dropped too far for fusion to continue. The reactions stopped. The proportions locked in approximately 75% hydrogen and 25% helium by mass, with trace amounts of lithium and essentially nothing heavier. Here is what makes that number remarkable. Astronomers today can measure the composition of the oldest, most chemically pristine stars. Stars that formed in the early universe from nearly unprocessed primordial gas. The ratio they find is approximately 75% hydrogen to 25% helium. The prediction from Big Bang nucleosynthesis theory and the observation from ancient stellar spectra agree with striking precision. The universe carries the chemical record of its first 3 minutes written into the composition of its oldest stars, and those stars still exist, still burning, still confirming what happened before any planet or galaxy had formed. But the universe at 20 minutes old was still nothing like the universe today. It was still overwhelmingly hot, still an opaque plasma, still a place where light could not travel more than a microscopic distance without colliding with a free electron and scattering in a random direction. For hundreds of thousands of years, the cosmos was a fog, glowing intensely, filled with energy, but structurally blind. Information could not propagate. No signal could carry across distance. Every photon was trapped, pinballing through an endless maze of charged particles going nowhere. Then, approximately 380,000 years after the Big Bang, the universe crossed a threshold. The temperature had fallen to roughly 3,000 Kelvin. At that level, electrons no longer had enough kinetic energy to escape the electromagnetic pull of atomic nuclei. For the first time in cosmic history, protons captured electrons and became neutral hydrogen atoms. Helium nuclei did the same. Matter across the entire observable universe became electrically neutral almost simultaneously. The effect on light was instantaneous and total. Neutral atoms do not scatter photons the way free electrons do. The fog that had persisted for 380,000 years simply cleared. Every photon that had been trapped, bouncing endlessly through the plasma, was suddenly free to travel in a straight line. The universe became transparent in what was on cosmic timescales, essentially a single moment. If something had been present to witness it, and nothing complex enough to witness anything existed yet, the experience would have been extraordinary. In every direction the sky was glowing, not with stars, not with galaxies, but with the thermal emission of a universe-wide plasma cooling through 3,000 Kelvin. Deep orange-red light uniform in every direction extending to infinity. No darkness anywhere. No shadows, no contrast. No variation except for the faintest ripples of density, 1 part in 100,000, that would one day grow into the large-scale structure of the cosmos. Everything glowing the same dim, ancient red. Beautiful in a way that has no human equivalent, and completely, utterly inhospitable to anything that might have tried to exist within it. That light was released 380,000 years after the beginning of everything. It has been traveling ever since, uninterrupted, crossing the expanding universe in every direction for nearly 13.8 billion years. It has not disappeared. It has not been absorbed. It is still here, stretched by the expansion of space from visible orange-red wavelengths into the microwave spectrum, cooled from 3000 Kelvin down to 2.725 Kelvin. Invisible to any biological eye, but detectable by the right instruments. It is the reason the universe has a temperature floor. It is the origin of the number that sets the coldest achievable equilibrium for any object anywhere in observable space. 2.7. Kelvin is not an arbitrary physical constant. It is the age of the universe written in degrees. That light still exists. It surrounds you right now, you just cannot see it. That is the story of what comes next. In 1964, two radio engineers at Bell Telephone Laboratories in Holmdel, New Jersey, were trying to build the most sensitive microwave antenna ever constructed. Arno Penzias and Robert Wilson were not cosmologists. They were not hunting for the origins of the universe. They were communications engineers with a practical goal: characterize the noise floor of a large horn-shaped antenna originally built to track the Echo satellite, and make it as clean as possible for future telecommunications work. Sensitive instruments pick up everything. The antenna was no exception. Penzias and Wilson identified every source of interference they could find. Radio transmissions from New York City, thermal noise from the electronics radiation from the Milky Way when the antenna pointed along the galactic plane. They accounted for each one, subtracted it from their data, and moved on. Methodical, patient, precise. But one signal refused to leave. A faint, persistent hiss remained in every measurement, regardless of what they did. They pointed the antenna at different parts of the sky. The hiss was there. They waited for different seasons, reasoning that some terrestrial sources might be stronger in summer or winter. The hiss did not change. They measured at different times of day and night. Identical. The signal was perfectly uniform in every direction, constant across time, arriving at equal intensity from every point on the sky. It corresponded to a thermal source at approximately 3.5 Kelvin, just above absolute zero, in a frequency range that had no obvious explanation from any known astronomical or terrestrial origin. They considered every possibility. The antenna itself might be generating thermal noise. They recalibrated every component. The hiss remained. Some contamination on the reflective surface might be contributing broadband emission. They inspected the horn carefully and discovered that a pair of pigeons had been nesting inside the structure-coating portions of the interior with what Penzias later described in the driest possible scientific language as a white, dielectric material. They climbed inside the antenna and removed the pigeons. They scraped out the accumulation. They remeasured. The hiss was still there. At this point, most engineers would have concluded the instrument had an irreducible noise floor and moved on. Penzias and Wilson were bothered by it. The signal was too clean, too uniform, too perfectly isotropic to be instrumental noise, which typically has directional or frequency characteristics that betray its origin. This hiss came from everywhere equally. That was strange enough to keep pulling at them. Meanwhile, 40 miles away at Princeton University, a group of theoretical physicists was actively searching for exactly this signal. Robert Dicke, Jim Peebles, and their colleagues had been working through the implications of Big Bang cosmology and had independently predicted that if the universe began in an extremely hot, dense state, it should have left behind a residual thermal radiation field, filling all of space, a faint microwave glow, corresponding to a temperature of a few degrees above absolute zero. They were in the process of building their own antenna specifically to detect it. When a mutual contact connected the two groups, Dick reportedly put down the phone, turned to his colleagues and said, "We've been scooped." The persisting hiss in the Bell Labs antenna was not instrument noise. It was not pigeon contamination. It was the oldest light in the universe, photons that had been traveling through expanding space for nearly 13.8 billion years, arriving at a telecommunications antenna in New Jersey and being mistaken briefly for a calibration problem. The discovery was published in 1965. Penzias and Wilson described the signal in careful, understated language, noting the excess antenna temperature they could not account for. A companion paper by the Princeton Group provided the cosmological interpretation. The two papers together announced one of the most significant observational results in the history of science: direct detection of the thermal afterglow of the Big Bang, confirming that the universe had a hot, dense origin and has been expanding and cooling ever since. In 1978, Penzias and Wilson received the Nobel Prize in Physics. The committee's citation described the discovery as the most important cosmological finding since Edwin Hubble demonstrated that galaxies are receding and the universe is expanding. That comparison is not hyperbole. Hubble's observation established that the universe has a history. The cosmic microwave background proved that history began in fire. It is worth pausing on the specific role that pigeon droppings played in this sequence of events. Penzias and Wilson spent real time with real equipment, carefully removing biological waste from the interior of a scientific instrument as part of their attempt to measure the temperature of the early universe. They did not know that was what they were doing. But the act of elimination, ruling out every mundane explanation one by one until only the extraordinary one remained, is exactly how the discovery worked. The pigeons did not help, but they did not prevent it either. They were simply one more item on the checklist, and the checklist was thorough enough to survive them. This is the only time in the history of science that pigeon droppings played a role in the discovery of the origin of the cosmos. That fact deserves to be acknowledged with the mixture of absurdity and reverence it warrants. But the initial detection was only the surface of the iceberg. What lies hidden beneath that 2.7 Kelvin signal is what actually changed everything. The 1965 detection established that the cosmic microwave background existed. What it could not do was characterize it in any detail. The measurement tools available to Penzias and Wilson were sensitive enough to find the signal, but nowhere near precise enough to examine its structure. For 2 decades, the background remained a confirmed but poorly understood object. Its temperature known within a degree or so, its uniformity assumed, but not rigorously tested. Its subtler properties entirely invisible. That changed in November 1989, when NASA launched the Cosmic Background Explorer satellite known as COBE. COBE carried instruments designed from the ground up for a single purpose: to measure the cosmic microwave background with a precision no ground-based antenna could achieve. Earth's atmosphere absorbs and emits microwaves, contaminating any measurement made from the surface. Above the atmosphere, those confounding emissions disappear entirely, and the signal can be measured in its pure form. COBE operated at an altitude where the atmosphere was no longer a factor, and the results it returned were extraordinary on 2 separate levels. The first result confirmed the theoretical prediction with a precision that stunned the physics community. The spectrum of the cosmic microwave background, the pattern of intensity across different microwave wavelengths, matched the mathematical curve of a perfect blackbody radiator with a closeness that had never been observed in any natural phenomenon before. A blackbody is an idealized object that absorbs all incoming radiation and emits energy in a specific, temperature-dependent pattern governed entirely by the laws of thermodynamics. Real objects approximate this curve to varying degrees. The cosmic microwave background matched it so precisely that when the COBE data was presented at a meeting of the American Astronomical Society in 1990, the audience gave a standing ovation, physicists standing, applauding. For a graph, the curve was that clean. This meant the early universe had been in near-perfect thermal equilibrium, hot, dense, uniform, and well mixed exactly as Big Bang theory predicted. The temperature was pinned at 2.725 Kelvin, with uncertainty smaller than 1/1000th of a degree. The first major quantitative result from COBE was in effect the most precise thermometer reading ever taken of an object 13.8 billion years old. The second result was more significant still. COBE detected tiny temperature fluctuations across the sky, variations of approximately 1 part in 100,000 in the background temperature. some directions fractionally warmer than average, others fractionally cooler. The differences were so small that detecting them required subtracting the much larger effects of Earth's motion through space, the Milky Way's own emission, and the dipole pattern caused by the solar system's motion relative to the background. What remained after all that subtraction was a map of the early universe's density structure at 380,000 years of age. 1 part in 100,000. That is the difference between a region of the sky at 2.725 Kelvin and a region at 2.72501 Kelvin. Detecting it from orbit, in the presence of all the other signals that had to be removed, was a feat of engineering and data analysis that took years of work to accomplish. The mission then continued, and each subsequent generation of instruments pushed further. The Wilkinson Microwave Anisotropy Probe (WMAP), launched in 2001, with angular resolution roughly 35 times finer than COBE. Where COBE could see broad patches of temperature variation, WMAP could resolve the detailed structure and the specific sizes and distributions of the warm and cool spots, the pattern of peaks and valleys in the fluctuation spectrum. From that pattern, measured with careful statistics, came numbers that had no business being determinable from microwave maps of the ancient sky. The age of the universe, 13.77 billion years. The fraction of the universe's total energy content made of ordinary matter, atoms, molecules, everything visible, 4.6%. The fraction made of dark matter, which interacts gravitationally but not electromagnetically and has never been directly detected, 23%. The fraction made of dark energy, the mysterious component driving the accelerating expansion of space, 72%. All of these numbers extracted from temperature variations smaller than any thermometer on Earth could detect in radiation that has been traveling since before the first star ignited. Then, the European Space Agency's Planck satellite, launched in 2009, refined everything further. 9 frequency bands, sensitivity and angular resolution that surpassed WMAP by significant margins. The age of the universe recalibrated to 13.798 billion years. The background temperature confirmed at 2.725 Kelvin. The proportions of ordinary matter, dark matter, and dark energy measured with percent-level precision. The geometry of the universe confirmed to be flat, meaning parallel lines remain parallel across cosmic distances, and the angles of a triangle sum to exactly 180 degrees. And something else, a tension in the measurement of the Hubble constant, the rate at which the universe is expanding, that disagreed with measurements made by other methods. That tension remains unresolved. It may require new physics to explain. 3 satellite missions. 30 years. The faint hiss that annoyed 2 engineers in New Jersey became the single most informative observation in the history of cosmology. Reading the cosmic microwave background is something like finding a sheet of paper that burned 13.8 billion years ago and discovering that the char pattern left behind encodes the fingerprint of whoever lit the match, the temperature of the room, the composition of the atmosphere, and a map of where every piece of furniture was standing. The paper is gone, but the ash, read carefully enough, remembers everything. If you could see the cosmic microwave background with your naked eyes, if human vision extended into the microwave spectrum, the entire sky would glow with a faint, uniform light, slightly warmer in some directions, slightly cooler in others. The whole pattern shimmering at a temperature barely above absolute zero. What would that look like to you? A dim, endless glow in every direction with no stars, no darkness, no edge. The oldest wallpaper in existence, covering the entire observable universe, every surface, every direction, inescapably present. Those 1 in 100,000 fluctuations in the cosmic microwave background are not just data, they are the seeds of every galaxy, every star, every planet, and you. Before the universe became transparent, before a single photon traveled freely in a straight line, the primordial plasma was not silent. it was singing. In the 380,000 years between the Big Bang and recombination, the universe was a hot, dense mixture of ordinary matter, dark matter, and radiation, all packed tightly enough that pressure and gravity were in constant competition. Gravity pulled matter together into denser clumps. Radiation pressure pushed back outward, resisting compression. The result of that tug-of-war was not a static standoff. It was oscillation. Spherical pressure waves rippled outward through the plasma compressions, followed by rarefactions. The same physical mechanism as sound waves in air, except the medium was the entire early universe, and the waves traveled at a speed equal to approximately 57% of the speed of light. That is not a metaphor. Those were real acoustic waves propagating through real matter carrying real energy. The early universe had a sound, and it was enormous. Each wave originated from a slight overdensity in the primordial distribution of matter. Those 1 in 100,000 fluctuations imprinted by quantum processes in the earliest moments after the Big Bang. At each of those overdense points, a spherical pressure wave began propagating outward through the plasma. For 380,000 years, these waves traveled, expanding at 57% of the speed of light. Then, recombination happened. The plasma turned transparent. The radiation decoupled from the matter and streamed away freely. The pressure that had been driving the waves vanished. The waves stopped, their leading edges frozen in place at whatever distance they had reached in 380,000 years of travel, became permanent features of the matter distribution. The distance those waves had traveled by the moment they stopped, the radius of the sound horizon at recombination, corresponds to a physical scale that has been stretching with the expansion of the universe ever since. Today, that characteristic scale measures approximately 490 million light-years. It is not a wall, not a visible structure, but a statistical preference across the universe. Pairs of galaxies are slightly more likely to be separated by roughly 490 million light-years than by distances somewhat smaller or larger. The acoustic signature of those ancient pressure waves still shapes where galaxies live today. This phenomenon has a name: baryon acoustic oscillations, abbreviated BAO. And it has become one of the most powerful tools in modern cosmology, functioning as a standard ruler for measuring cosmic distances. Because physicists can calculate the expected size of the BAO scale from first principles from the known physics of the early universe, and then measure it in the observed distribution of galaxies, they can use the apparent angular size of that feature on the sky to determine how far away those galaxy populations are, and from that, how the universe has been expanding over time. BAO measurements have been used to constrain the properties of dark energy, cross-check the cosmic distance ladder, and map the expansion history of the universe across billions of years. The practical implication of this is worth sitting with. Large-scale Galaxy surveys the Sloan Digital Sky Survey, the dark energy spectroscopic instrument. The upcoming Euclid mission are mapping the positions of hundreds of millions of galaxies across cosmic distances, not primarily to count to them, but to measure a subtle clustering preference imprinted by sound waves that stopped propagating nearly 14 billion years ago. The structure of the modern universe at its largest scales is an archaeological artifact of acoustics. Think of the universe as a musical instrument built at the moment of creation. It had one brief window, 380,000 years, during which it could vibrate. A single sustained chord played across the entire cosmos at once, with wavelengths measured in hundreds of millions of light-years. Then the instrument was silenced by recombination, the energy that drove the vibrations streaming away as light. What remained was not the sound itself, but the frozen pattern of its final state. The compressions and rarefactions locked into the matter distribution at the exact moment the music stopped. Galaxies today do not know they are following an acoustic template. They simply formed where gravity pulled matter together, and gravity was stronger where the ancient waves had left density peaks. The sound shaped the landscape. The landscape shaped the galaxies. and the galaxies distributed across the observable universe in their statistically preferred separations carry the echo of a note played when the universe was less than 400,000 years old. Every time astronomers map the large-scale distribution of galaxies and find that characteristic clustering scale, every time the BAO signal appears in a new survey of a different patch of sky at a different cosmic epoch in data, collected by instruments that did not exist when the theory was first proposed, it is confirmation that the structure of everything we can see was choreographed by sound, not metaphorically, physically, causally. That keeps me awake at night in a way that most physics does not. Not because it is disturbing exactly, but because the scale of the implication refuses to shrink no matter how many times it is encountered. The universe we live in, its walls and voids, its galaxy clusters and filaments. The very reason the Milky Way exists where it does is the frozen consequence of a sound that no ear could have heard in a medium that no longer exists, playing in a universe that looked nothing like this one, and we can measure it. Today, with telescopes pointed at galaxies, where are the galaxies shaped by that ancient sound? And more importantly, how much of the universe do they actually occupy? Pull back far enough from any individual galaxy, far enough that the Milky Way shrinks to a point of light, indistinguishable from its neighbors, and the universe reveals its true large-scale architecture. It does not look like a uniform scattering of galaxies through space. It looks like foam. Thin, bright sheets and filaments of galaxies surround vast, dark, nearly empty regions. The structure has a name, the cosmic web, and its defining feature is not the bright parts, it is the dark ones. Galaxies do not distribute themselves evenly through space. They cluster along the intersections and surfaces of enormous structural features, filaments stretching for hundreds of millions of light-years walls, where multiple filaments converge, and at the densest intersections, clusters and superclusters containing thousands of galaxies bound together by gravity. These are the bright threads of the web. Between them lie the voids. A cosmic void is not simply a region with fewer galaxies. It is a region with almost none. The density of matter inside a typical void runs at roughly 10 to 20% of the cosmic average. Not half as dense, not a quarter as dense, but an order of magnitude below the mean. A few isolated dwarf galaxies drift through the interior of most voids. But they are so widely separated that traveling from one to the next would require crossing tens of millions of light-years of essentially uninterrupted vacuum. The Boötes void is one of the most striking examples known. Discovered in 1981, it stretches approximately 330 million light-years across its widest dimension. Inside that volume, large enough to contain thousands of galaxy clusters, if it were filled to average cosmic density, there are fewer than 60 known galaxies. The local group, the small cluster containing the Milky Way, Andromeda and their satellite galaxies, packs more than 50 galaxies into a region just 10 million light-years across. The Boötes void is 33 times wider and contains roughly the same number. The implications of that emptiness are not merely geometric. If the solar system were located inside the Boötes void, rather than in its actual position within the Milky Way, the history of astronomy would have unfolded completely differently. Every telescope ever built would have looked outward through 330 million light-years of near-total emptiness before reaching the nearest concentration of external galaxies. Edwin Hubble's discovery that galaxies beyond the Milky Way exist made in 1923 using the 100-inch Hooker telescope at Mount Wilson would not have been possible with any technology available in the 20th century. The evidence for cosmic expansion would have been inaccessible. The Big Bang model might not have been developed until instruments of 21st century sensitivity became available. The entire trajectory of modern cosmology could have been delayed by decades or more, simply because of where in space the solar system happened to form. That dependence on location for what is even scientifically discoverable is unsettling in a quiet way. We know what we know, partly because we happen to live in a relatively well-populated region of the universe. somewhere in the Bota's void, if any civilization existed there, and the probability is vanishingly small, their cosmology would look radically different from ours. Not because the physics differs, but because the observable evidence available to them does. Cosmic voids are not rare anomalies. They are the dominant structure of the observable universe by volume. Surveys, mapping the three-dimensional distribution of galaxies across hundreds of millions of light-years, consistently find that voids occupy between 80 and 90% of the total volume. The filaments, walls, and clusters where galaxies actually live are compressed into the remaining 10 to 20% thin, bright structures wound around the surfaces of vast empty bubbles. The web looks impressive in maps and visualizations, all those glowing filaments tracing out the skeleton of cosmic structure. But the web is mostly holes. The filaments are thin threads stretched across spaces that dwarf them. Inside those voids, the thermal environment is as close to pure as the universe offers. No significant local radiation sources. No nearby stars, no active galactic nuclei within meaningful range, no supernova remnants heating the surrounding medium. The temperature inside a cosmic void for any isolated object floating through it with no internal heat source converges on 2.7 Kelvin. Not approximately, not nearly, precisely because there is nothing else contributing. The cosmic microwave background is the only radiation field present in any meaningful quantity, and it alone sets the equilibrium. Pick a random point anywhere in the observable universe. Not a point biased toward galaxies or clusters, a genuinely random coordinate within the full volume of space that light has had time to reach since the Big Bang. The overwhelming probability, somewhere between 80 and 90%, is that the point falls inside a void, cold, dark, empty, in a way that makes the vacuum of Earth orbit look busy, bathed in a microwave glow at 2.7 Kelvin that has been unchanged for billions of years and will remain unchanged for billions more. No gradient, no transition, no event, just the baseline temperature of existence holding steady across distances that reduce the distances between stars to trivialities. This is the default condition of the universe, not the exception. The cosmic web's bright filaments, beautiful as they are in false color maps, impressive as they are, as concentrations of billions of galaxies represent a minority of space crowded into a fraction of the total volume, while the voids expand, grow, and slowly hollow out the web from within as the accelerating expansion of space stretches the large-scale structure ever further apart. The voids are winning. They have been since shortly after the Big Bang, and their temperature tells the story 2.7 Kelvin uniform, featureless, patient. The default answer to the question of what the universe is like when nothing interesting is happening nearby. But even within the filaments and galaxies, the most crowded places the universe has to offer, the vast majority of the volume is still cold vacuum. And that leads to the most important question of all: just how rare is warmth really? The numbers exist. They have been calculated, cross-checked, published in peer-reviewed literature, and confirmed by multiple independent methods. The problem is not their accuracy. The problem is that the human mind was not built to hold them. Start with the observable universe. The region of space from which light has had time to reach Earth since the Big Bang spans a radius of approximately 46.5 billion light-years in every direction. Converting that into cubic meters produces a number so large that writing it out in full requires 81 digits, approximately 4.2 times 10 to the power of 80 cubic meters. That is the total volume of everything we can, in principle, observe. Every galaxy survey ever conducted, every cosmological measurement ever made, every photon ever detected by every telescope ever built. All of it samples from within that volume. Now, consider the stars. The observable universe contains an estimated 1 times 10 to the power of 24 stars, a number that itself defies casual comprehension, roughly 10 times the number of grains of sand on every beach and ocean floor on Earth. Combined, Each star has a volume. Our Sun, a medium-sized star by galactic standards, has a volume of approximately 1.4 times 10 to the power of 27 cubic meters, averaged across the full stellar population, which includes everything from red dwarfs considerably smaller than the Sun to blue supergiants many times larger. A reasonable mean stellar volume runs somewhat below the Sun's. Multiply estimated stellar count by average stellar volume, and the total comes to approximately 10 to the power of 51 cubic meters. This is the combined interior volume of every star in the observable universe. Every nuclear furnace, every thermonuclear reaction converting hydrogen to helium, every source of stellar energy that has ever existed within the range of our instruments, added together. Divide that by the total volume of the observable universe. The result is approximately 10 to the power of negative 29, written as a fraction, 1 divided by 1, followed by 29 zeros. The hot interiors of all stars combined occupy less than 1/1000th of 1/1000th of 1/1000th of the total volume of observable space. Not 1%. Not 1 part per million. Not 1 part per trillion. 1 part in 10 to the 29th power. Do you actually understand that number? Most people say yes and mean no. So try this. The Pacific Ocean contains approximately 7 times 10 to the power of 17 cubic meters of water, roughly 700 million cubic kilometers. It is the largest single body of water on Earth's surface, covering more area than all the land on the planet combined. Now imagine that the Pacific Ocean represents the total volume of the observable universe. On that scale, the combined volume of every stellar interior, every point in space hot enough for nuclear fusion, every place where temperatures reach millions of degrees would be represented by a single molecule of water. Not a drop, not a grain of salt. One molecule somewhere in the Pacific. That is the fraction of the universe occupied by anything hot enough to qualify as the interior of a star. Everything else in that analogy is ocean. Cold, dark, close to 2.7 Kelvin, stretching in every direction without interruption, for distances that make the volume of the Pacific look like a rounding error in the other direction. And stellar interiors are not the relevant threshold for warmth in any biological sense. A star's interior at millions of degrees is not where life lives. The relevant question, the one that connects cosmic temperature to the existence of anything like human experience, concerns liquid water, complex chemistry, the narrow band of conditions where molecules can interact with enough energy to build structure, but not so much energy that they are immediately destroyed. Life, as it is understood, requires temperatures roughly between the freezing and boiling points of water at habitable pressures, a range spanning less than 100 degrees Celsius on a temperature scale that runs from absolute zero to tens of millions of degrees in stellar interiors. Habitable zones, the orbital bands around stars, where a rocky planet with the right atmosphere could maintain liquid water on its surface, are narrow rings. For a Sun-like star, the habitable zone spans a range of roughly 0.7 to 1.4 astronomical units, a band perhaps 70 million miles wide. Set against the average distance between neighboring stars of roughly 4 light-years, approximately 24 trillion miles, the habitable zone occupies a fraction of interstellar space, smaller than the stellar volume fraction, by many additional orders of magnitude, and that is before accounting for the requirement that a planet actually exist within that zone, that it have the right mass, the right atmosphere, the right geological history. Each additional filter reduces the count further. The volume of space genuinely warm enough for liquid water chemistry occupied by a world with conditions compatible with the biology we understand is a fraction of the total cosmic volume, so small that 10 to the negative 29 begins to look generous by comparison. There is no tidy exponent for it. The numerator, every warm, wet, biologically active surface that may exist across all 2 trillion observable galaxies, is real and may include many billions of worlds. The denominator is 4.2 times 10 to the 80th cubic meters of mostly cold, mostly empty, mostly 2.7 Kelvin void. The fraction vanishes into notation. This is not pessimism, it is arithmetic. The universe does not owe warmth to its contents. It does not allocate heat proportionally to volume. It generates heat locally, in the specific locations where gravity has compressed matter to the ignition threshold of nuclear fusion, and it allows that heat to radiate outward until it dilutes into the background. The background wins every time, everywhere, by a margin that requires scientific notation with negative exponents to express, and requires the Pacific Ocean as a visual aid to even partially communicate. What makes this calculation something more than an academic exercise is the thing it implies about every warm place in the universe. Warmth is not a background condition. It is not the normal state of matter in space. It is a local, temporary, physically demanding exception that requires a star, an orbit, a planet, an atmosphere, a magnetic field, a geological cycle, and a precise combination of all of them maintained across billions of years. Every one of those conditions narrows the fraction further. Every requirement that must be met simultaneously is another factor in the denominator. The number 10 to the negative 29th measures only the hot volume. It says nothing about how long that volume stays hot. It says nothing about whether any of those stellar interiors are warming surfaces where water can pool and chemistry can build. It says nothing about time. That number measures only space. What comes next measures something more frightening: time. The universe is 13.8 billion years old. Stars have been burning for approximately 13.5 billion of those years, igniting a few 100 million years after the Big Bang, from the first generation of hydrogen and helium clouds massive enough to collapse under their own gravity. From a human perspective, that is essentially the entire history of everything. Stars have always been there. In any meaningful sense of the word, always, that fits inside a human lifetime or a civilization's memory. But from the perspective of cosmic time, the era of starlight is not essentially everything. It is a brief opening act that has barely begun and is already past its peak. The rate of star formation in the universe reached its maximum roughly 10 billion years ago, a period astronomers sometimes call cosmic noon, when galaxies were actively converting gas into stars at rates far higher than anything seen today. Since then, the rate has been declining. The Milky Way currently forms new stars at a rate of roughly 2 to 3 solar masses per year, a fraction of what it produced during its most productive epochs. The raw material is being consumed faster than new supplies are becoming available. Galaxies are not running out immediately, but the trend is clear and irreversible. The universe has been gradually dimming for the last 10 billion years. Most stars burning today, and the vast majority of stars that will ever burn, are red dwarfs. These are small, cool, extraordinarily frugal objects, burning hydrogen at such a conservative rate that their lifespans extend far beyond anything a sun-like star can achieve. The most long-lived red dwarfs, those at the lower end of the stellar mass range, will continue fusing hydrogen for approximately 10 to 15 trillion years. That is 1,000 times the current age of the universe. Every red dwarf that has ever formed is still burning today. Not one has yet exhausted its fuel, not one has died. They are, in the most literal sense, just getting started. But even they will eventually run out. When the last red dwarf exhausts its hydrogen, the era of nuclear fusion ends. No new stars ignite after that point, because the raw material cold hydrogen gas in sufficient concentrations will have been either consumed or dispersed. What follows is the degenerate era, a period dominated not by burning stars, but by their cooling remnants. White dwarfs, the compressed carbon-oxygen cores left behind when stars like the sun shed. Their outer layers will persist for trillions upon trillions of years, slowly radiating away their residual heat into the void. They produce no new energy. They are embers, not fires. Over timescales, measured in quadrillions of years, they fade from white to yellow to dim red to infrared, approaching but never quite reaching the temperature of the cosmic background. Neutron stars cool on similar timescales, shedding their rotational and thermal energy through electromagnetic radiation until they too become dark remnants, drifting through an increasingly empty and cold universe. Then come the black holes. Quantum mechanics predicts, and the physics community broadly accepts, though direct observational confirmation remains elusive, that black holes are not perfectly black. They emit a faint thermal radiation called Hawking radiation, named for Stephen Hawking, who derived the theoretical result in 1974. The rate of emission is extraordinarily small for large black holes, and the process operates over timescales that are almost impossible to express in meaningful terms. A black hole with the mass of the Sun would take approximately 2 × 10 to the power of 67 years to evaporate completely through Hawking radiation. A supermassive black hole at the center of a large galaxy, containing billions of solar masses, would require approximately 10 to the power of 100 years, 1 Google years, to evaporate entirely. 1 Google years, the number that gave Google its name, repurposed as a unit of cosmic time, measuring how long the universe will persist in any recognizable structured form. Now compress the entire future history of the universe into a single calendar year. Every second of that year represents an enormous span of actual time scaled so that the evaporation of the last black hole falls on December 31st at midnight. On this scale, where does the era of starlight, the entire period during which nuclear fusion exists, including right now, including every star that has ever burned or will ever burn, fall? It ends in the first fraction of a second after midnight on January 1st. Not the first day, not the first hour, the first fraction of a second. Everything that has ever been illuminated by starlight, every photon ever emitted by any star, every warm planet that has ever existed, every moment of biological evolution powered by stellar energy across the entire observable universe, all of it is compressed into a sliver of time so small it would require a high-speed camera to capture. The remaining 364 days, 23 hours, 59 minutes, and nearly 60 seconds of that year pass in total darkness, no fusion, no starlight, just the slow cooling of remnants and the even slower evaporation of black holes, all trending inexorably toward a cold, featureless equilibrium. The era of warmth is not just brief. It is brief in a way that the word brief was not designed to convey. So where does Earth, the only warm world we know with certainty, stand within this immense timeline? Earth is warm. That sentence contains more improbability than it appears to. Not warm the way a star is warm through ongoing nuclear fusion in a compressed core. Warm in a far more fragile sense. Warm enough on its surface, consistently enough over geological time, to keep water liquid, maintain a stable atmosphere, and permit the slow accumulation of biological complexity across 4 billion years. That particular kind of warmth is not a default. It is the outcome of a chain of physical requirements, so specific, so simultaneous, and so interdependent that examining the list honestly produces something between gratitude and vertigo. Start with the star. The Sun is a G-type main sequence star, middle-aged, middle-mass burning hydrogen at a steady and moderate rate, with a luminosity that has remained within a relatively narrow range for 4.5 billion years, will continue to do so for roughly 5 billion more. This stability matters enormously. A star, 10% more massive than the Sun, burns hotter and exhausts its fuel faster, potentially dying before complex life has time to evolve. A star, significantly less massive, emits most of its energy in the infrared, which creates different photochemical conditions in any orbiting atmosphere and typically forces habitable planets so close to the star that tidal locking becomes a serious concern. The Sun's mass is not optimal by design, but it happens to fall in a range compatible with long-term surface habitability, and that is not a trivial accident. Then there is the orbit. Earth sits at approximately 1 astronomical unit from the Sun, roughly 93 million miles. The Sun's habitable zone, the orbital band where a rocky planet with Earth-like atmospheric properties could maintain liquid water on its surface, spans approximately 70 million miles in width. Earth threads through that band. Move it inward by a few percent, and the oceans begin evaporating. Water vapor accumulates in the upper atmosphere, and a runaway greenhouse effect becomes self-sustaining. Move it outward by a few percent, and global glaciation becomes possible, potentially triggering an ice albedo feedback that freezes the planet entirely. 70 million miles sounds like a generous margin. Set it against the 25 trillion miles separating the Sun from its nearest stellar neighbor, and the habitable zone occupies a fraction of that interstellar distance, too small to describe without scientific notation. Mass matters next. Earth is large enough to retain a nitrogen-oxygen atmosphere against solar wind erosion over geological time, but not so large that it accumulated a thick hydrogen-helium envelope during formation, which would have produced a very different surface environment. The mass also drives internal heat. Earth's interior remains partially molten 4.5 billion years after formation, sustaining the convection currents in the liquid outer core that generate the magnetic field. That magnetic field is not decorative. It deflects the charged particle stream of the solar wind, which would otherwise strip the upper atmosphere away over millions of years. Mars provides the instructive comparison. Mars once had a magnetic field. It also once had a substantially thicker atmosphere and strong evidence. Valley networks, ancient lake beds, mineralogy, consistent with prolonged liquid water, suggests it once had surface water as well. Sometime in the first 1 or 2 billion years of solar system history, Mars's interior cooled enough that its core solidified, the magnetic dynamo failed, and the field collapsed. The solar wind went to work on the atmosphere directly. Over hundreds of millions of years, it eroded away. The pressure dropped. Liquid water became impossible. Mars went from a world that might, under different circumstances, have developed complex chemistry to the frozen, desiccated, radiation-bathed surface it presents today. Same solar system, same era, dramatically different outcome traced back to a planetary interior that cooled too fast. Venus demonstrates the other failure mode. Roughly similar in size and mass to Earth, in an orbit only about 30% closer to the Sun, Venus might intuitively seem like a near miss at habitability. It is not near anything. Its surface temperature averages 465 degrees Celsius. Hot enough to melt lead with room to spare. Hot enough to destroy any spacecraft that lands on it within a few hours. The cause is a runaway greenhouse effect. An atmosphere of dense carbon dioxide trapping solar radiation with such efficiency that the surface bakes continuously. Whether Venus was ever habitable in its early history remains debated, but whatever conditions existed then, they are entirely gone now. The same solar energy that sustains life on Earth has turned Venus into a furnace that makes the phrase hostile environment seem inadequate. Beyond magnetic fields and atmospheres, Earth's long-term thermal stability also depends on the carbonate-silicate cycle, a geological thermostat operating over millions of years where volcanic outgassing adds carbon dioxide to the atmosphere and weathering of silicate rocks removes. This cycle has buffered Earth's temperature through ice ages, large igneous province events, and asteroid impacts that would otherwise have driven permanent climate shifts. Remove the geological activity that drives it, and the thermostat fails. Add to this the Moon. Earth's axial tilt, the angle at which the planet's rotation axis leans relative to its orbital plane, determines how extreme the seasons are. Mars, without a large moon to stabilize it, experiences chaotic variations in axial tilt over millions of years, ranging from nearly 0 to over 60 degrees. Earth's tilt has remained relatively stable, between about 22 and 24.5 degrees, over hundreds of millions of years, largely because the Moon's gravitational influence damps the wobble. Stable tilt means stable seasonal patterns. Stable seasonal patterns mean more predictable long-term climate. Jupiter finally sits in the outer solar system, at 5.2 astronomical units from the Sun, massive enough to gravitationally deflect or capture a significant fraction of the comets and asteroids that would otherwise enter the inner solar system far more frequently. Without Jupiter's influence, the rate of large impacts on Earth over its history would likely have been substantially higher. Every time this list is read carefully, the star, the orbit, the mass, the atmosphere, the magnetic field, the geological cycle, the water abundance, the moon, the outer giant planet, the response that feels most honest is not wonder alone. It is wonder mixed with something close to alarm. Each item is necessary. None is guaranteed. All of them had to be true, simultaneously sustained, over billions of years. For the surface of this particular rock to remain warm enough for water to stay liquid. But that luck does not last forever. And Earth's ending has been written into the physics since the very first day. Stars do not stay constant. They cannot. The physics of nuclear fusion inside a stellar core guarantees a slow, irreversible drift toward higher luminosity over a star's main sequence lifetime, as the gradual conversion of hydrogen to helium changes the core's composition and forces subtle structural adjustments. The Sun today is approximately 30% brighter than it was when Earth formed 4.5 billion years ago. That increase has been slow enough that life has adapted, but it has not stopped, and it will not stop. In approximately 1 billion years, solar output will have increased by roughly another 10% above current levels. That increment, modest as it sounds against the scale of stellar evolution, is enough to trigger a cascade that ends surface habitability on Earth permanently. As more solar energy reaches the planet, surface temperatures rise, warmer oceans evaporate more water. Water vapor is itself a greenhouse gas, one of the most effective ones in Earth's atmosphere, so more of it traps more heat, which drives more evaporation, which traps more heat. The feedback accelerates. Once ocean temperatures climb high enough to sustain this cycle without interruption, the process becomes self-sustaining and irreversible. The oceans do not boil away overnight. They evaporate over millions of years. The water vapor accumulating in the upper atmosphere, where ultraviolet radiation from the sun breaks the molecules apart, and the hydrogen too light to be retained by Earth's gravity escapes into space. The water does not return. The oceans are gone, permanently. What remains is a dry, hot surface under a thickened carbon dioxide atmosphere, stripped of the liquid water that has defined Earth's character for 4 billion years. Surface temperatures climb toward Venus-like conditions. Complex surface life and most subsurface life cannot survive. Whatever biology persists would be microbial, confined to specific extreme environments, and almost certainly on borrowed time. The window for the kind of life that can look up at the stars and ask questions about them closes approximately 1 billion years from now. In cosmic terms, 1 billion years is not long. It is roughly the same duration as the period from the formation of the first eukaryotic cells to the present day. By the timeline of life on Earth, it is an entire chapter of biological history. By the timeline of the universe, it is a rounding error. Then comes the larger ending. In approximately 5 billion years, the Sun will have exhausted the hydrogen fuel in its core. The core will begin to contract under gravity heating as it compresses, while the outer layers of the star expand dramatically in response. The Sun will swell into a red giant, its radius growing by a factor of roughly 200 over tens of millions of years. At its maximum extent, the Sun's outer envelope will extend to somewhere between the current orbits of Earth and Mars. Models disagree on whether Earth's orbit falls just inside or just outside the expanded solar surface, partly because Earth's orbital radius will itself have changed as the Sun loses mass during its giant phase. The question of whether Earth is physically engulfed may be technically open. Whether it remains habitable in any meaningful sense is not. Before the red giant phase even begins, the gradually increasing solar luminosity will have already rendered Earth uninhabitable for 1 billion years. The red giant expansion is not the cause of Earth's end. It is the final, dramatic confirmation of a process that will have concluded long before the sun's outer layers arrive. Zoom out from the solar system and the same aging process is visible at galactic scales. The Milky Way's star formation rate peaked approximately 10 billion years ago, when vast reserves of cold hydrogen gas were still available to collapse into new stars. Since that peak, the rate has been declining as the galaxy's gas supply is consumed. Today, the Milky Way forms stars at a rate far below its historical maximum. Other galaxies show similar patterns. The universe as a whole is forming stars more slowly now than at any point in its past, and the rate will continue to decline as gas reserves deplete further. The cosmos is not at the beginning of its stellar era, or even in the middle. It is past the peak, on the descending slope, gradually dimming. Earth is not being robbed of its warmth by some external force. It is consuming a finite resource that was allocated at formation, and is being drawn down on a schedule written into the physics of stellar evolution. The sun will provide warmth for a defined period. That period has a known calculable end. The warmth was never permanent. It was always a loan with a repayment date. There is something almost administratively absurd about this. The sun began converting hydrogen to helium 4.6 billion years ago. Every calculation of stellar evolution available to astrophysics has, in principle, contained the information that this process produces a slowly brightening star, whose eventual expansion will terminate the habitable conditions on its third planet. The termination notice was written into the initial conditions of the solar system at the moment of formation. It has been executing on schedule for 4.5 billion years. The sun sent its notice of contract termination 4.6 billion years ago. It simply has not been read yet. Standing before all of this, a cold universe, a short window, warmth this rare, what does existence on Earth actually mean? Right now, wherever this is being heard, the surrounding air temperature is approximately 20 degrees Celsius. Room temperature, the default setting of human habitation, so ordinary that it registers as nothing at all, background neutral, unremarkable. That temperature does not exist in 99.9999999% of the volume of the observable universe. The precise fraction of cosmic volume at or near 20 degrees Celsius, accounting for stellar surfaces, planetary atmospheres, volcanic environments, hydrothermal systems, is so small that expressing it meaningfully requires the kind of negative exponents that made the previous calculation feel abstract. 20 degrees Celsius is not a neutral temperature. It is an extreme outlier on the cosmic scale. It is the temperature of an exception so rare that the universe contains vast regions spanning hundreds of millions of light years where nothing has ever been this warm. Consider what is required to think about that fact. The human brain operates within a functional temperature range of approximately 35 to 40 degrees Celsius core temperature, not ambient. Drop below roughly 32 degrees and cognitive function degrades rapidly. Rise above approximately 42 degrees and proteins begin denaturing. Neurons stop firing correctly and the system fails within hours. The window in which a brain can process information and generate thought is less than 10 degrees wide. 10 degrees on a temperature scale that runs from absolute zero, -273 degrees Celsius, to the tens of millions of degrees found in stellar cores. The thermal band compatible with consciousness is vanishingly narrow, even before accounting for the spatial rarity of finding any planet within it. Every cell in a human body is at this moment actively working against entropy to maintain that temperature. Metabolism is not simply energy production, it is a continuous, high-precision thermal management operation. Mitochondria convert chemical energy into ATP and heat. Circulation distributes that heat through the body. Sweating and shivering and vasoconstriction modulate the output. The entire system expends a significant fraction of its energy budget on the single problem of staying warm enough to function while not becoming too warm to survive. Cells do not do this passively. They do it actively, continuously, at enormous metabolic cost every second of every day. Because the alternative is to drift toward equilibrium with the surrounding environment. And equilibrium at cosmic scales means 2.7 Kelvin. Every living thing on Earth is a small, temporary, energetically expensive argument against the default temperature of the universe. The entirety of human civilization, every city, every monument, every piece of art, every war, every scientific discovery, every moment of recorded history, from the first hieroglyphs carved in ancient Egypt to the last software update, uploaded to the International Space Station, has occurred within a span of roughly 10,000 years. On the timeline of Earth's history, 10,000 years is a thin layer of sediment, invisible in most geological formations. On the timeline of the universe, it is below the threshold of any meaningful unit of measurement. All of human civilization, everything humans have ever built or thought or destroyed, has happened inside a single, extraordinary and brief moment. A moment made possible entirely by the coincidence of a stable, middle-aged star, an orbit, at the right distance, and a planet that managed to hold on to its water and atmosphere long enough for biology to produce something capable of asking why. The cold is not an enemy. That framing is wrong, and it matters that it is wrong. The cold does not attack. It does not pursue. It is not hostile. It is simply the default, the state the universe returns to when no energy source is locally forcing it away from equilibrium. Cold is what space is when nothing interesting is happening. Warmth is what happens when something does, when gravity pulls matter together, when fusion ignites, when a planet forms at the right distance, when an atmosphere accumulates and holds. Warmth requires cause. Cold requires nothing. It is the baseline, the resting state, the answer the universe gives to any region left alone long enough. Every source of warmth in the universe is an ongoing effort against that baseline. Stars fuse hydrogen under enormous gravitational pressure because that pressure exists the moment it does not fusion, stops, and the remnant begins cooling. Planets stay warm because their stars continue burning and their interiors continue generating heat through radioactive decay processes that are themselves consuming finite fuel. Life stays warm because it eats and metabolizes and works every moment, without pause. The maintenance of warmth is not passive. It is never passive. It is always the product of something actively pushing back against the universe's overwhelming preference for cold. If the rarity of this warmth means anything, if the cosmic fraction 10 to the negative 29th, the narrow stellar era, the accidental alignment of conditions that produced a habitable Earth, if any of that registers, it might change. What deserves attention tomorrow? Not abstractly, concretely. The specific warmth available right now on this planet in this era. Dependent on a star that has roughly 1 billion years of habitable output remaining before its luminosity ends, the conditions we depend on is not guaranteed by anything in the laws of physics. What would you actually do tomorrow, knowing that this warmth, this specific, cosmically improbable, actively maintained warmth, is as rare as the numbers say it is? But before this ends, there is one final truth, one that even after everything just described can still make you sit down and reconsider everything from the beginning. After the last red dwarf burns out, after the last white dwarf fades below any detectable emission, after the last neutron star radiates away its rotational energy into silence, the black holes remain. They are the final structures, the last objects in the universe with any meaningful concentration of mass, any gravitational influence, any ability to organize matter around themselves. For timescales measured in numbers that make the current age of the universe look like a rounding error, the universe belongs to them. And then, one by one, they evaporate. Stephen Hawking demonstrated in 1974 that black holes are not perfectly black. Quantum mechanical effects near the event horizon, the boundary beyond which nothing can escape, cause black holes to emit a faint thermal radiation. The mechanism involves pairs of virtual particles spontaneously appearing near the horizon. One falls inward, one escapes outward, as real radiation, and the black hole loses a tiny, almost immeasurably small amount of mass in the process. The rate of emission is inversely proportional to the black hole's mass. Larger black holes radiate more slowly. For stellar mass black holes, the power output is so negligible that it will never be detected by any instrument conceivable from current physics. For supermassive black holes at galactic centers, the timescale to complete evaporation runs to approximately 10 to the power of 100 years. But eventually, not soon by any standard, but eventually with the certainty of physical law, the last black hole completes its evaporation. It releases a final burst of Hawking radiation, a brief flash of energy into the surrounding void, and then it is gone. No remnant, no residual structure, nothing left to mark where it was. At that moment, the universe contains photons drifting in every direction. Electrons and positrons scattered through an expanding space so vast that the average distance between any two particles is incomprehensible. Neutrinos, possibly depending on whether they have finite mass and decay over these timescales. Gravitational waves from ancient events. Their wavelength stretched by cosmic expansion into oscillations so slow they are effectively indistinguishable from flat spacetime. No atoms, no molecules, no chemistry, no structure at any scale from subatomic to cosmic. Just particles separated by distances that make the current voids between galaxy clusters look densely populated, all drifting apart in a universe that continues expanding, continues cooling, continues diluting, whatever remains toward a state of perfect total irrevocable sameness. This is what physicists call the heat death of the universe. The name is misleading in one important sense. The universe does not end in heat. It ends in the complete absence of any thermal difference. Every region of space reaches the same temperature. Every particle has the same average energy. There are no gradients left, no hot spot and cold spot separated by a temperature difference that could drive a flow of energy from one to the other. No difference of any kind that could cause anything to happen. This distinction is the most important one in all of thermodynamics, and it is the thing that makes heat death genuinely final in a way that mere coldness is not. Cold alone is not the end. Right now, the universe is 2.7 Kelvin across most of its volume, extraordinarily cold by any human standard, close to absolute zero, apparently near the worst possible condition. But 2.7 Kelvin spread across a universe that still contains stars, burning at millions of degrees, planets at hundreds of degrees, molecular clouds at tens of degrees, and the cosmic background at its baseline, that universe still has differences, still has gradients, still has energy flowing from hot regions to cold ones, from concentrated to diffuse, from structured to less structured. As long as those gradients exist, as long as any temperature difference remains anywhere, physics can happen, processes can run, something can occur. Cold with a gradient is still a universe where events are possible. A candle in a cold room can illuminate because there is a difference between the flame and the surrounding air. A star can radiate because there is a difference between its interior and the surrounding space. Life can exist because there is a difference between the chemical energy stored in food and the lower energy state of its metabolic products, and that difference can be exploited to do work, including the work of thinking. Take away the gradient, equalize everything, make every point in the universe identical in temperature and energy density. Now, nothing flows, nothing drives, nothing happens. Not because the temperature is near zero, it will be near zero at heat death, just as it is near zero in most of the universe today, but because there is no longer any difference to exploit. The machinery of physics requires a difference to run. Thermodynamics does not forbid a cold universe. It forbids a uniform one from doing anything. The universe at heat death is not colder than the universe today in any dramatically meaningful degree. It is a fraction of a Kelvin lower the cosmic background, continuing its slow descent as space expands. What changes is not primarily the temperature. What changes is the disappearance of every departure from that temperature. Every star, every planet, every biological process, every thought, all of it was a temporary deviation from uniformity. Heat death is when the last deviation closes. That is the thing that should actually be unsettling. Not the 2.7 Kelvin, not the stellar timescales, not even the 1 in 10 to the 29th fraction of cosmic volume that is warm. Those numbers describe a cold universe that is still by the standards of its ultimate fate, extraordinarily structured, extraordinarily varied, extraordinarily alive with process and difference and flow. The universe at 2.7 Kelvin right now is a thermodynamic paradise compared to what awaits it. The cosmic background temperature that seemed like the definition of cold at the beginning of this story turns out, from the vantage point of the far future, to describe a universe practically vibrating with order and complexity. Which raises the question that no physics currently answers. If heat death is the inevitable destination, if the second law of thermodynamics guarantees that entropy increases, that gradients close, that everything trends toward featureless uniformity, then the universe began in a state of extraordinarily low entropy, extraordinarily high order, a configuration so improbable, so precisely structured, so far from equilibrium, that the entire subsequent history of cosmic evolution is simply the process of that initial order dissipating. The wound-up spring, unwinding across 14 billion years and counting. The Big Bang did not just create matter and energy. It created an arrangement of matter and energy so far from equilibrium that a universe's worth of stars could burn, a universe's worth of galaxies could form, life could emerge, and think and ask questions. And all of that represents only a fraction of the available order being spent. Down. The spring was wound extremely tight. Who or what wound it? Physics describes the unwinding with extraordinary precision. It describes the initial conditions with measurements of increasing accuracy. What it does not explain is why those initial conditions were what they were. Why the universe began in a state of such improbably low entropy, rather than in a state already close to equilibrium, which would have produced a featureless, immediately, cold cosmos with no structure, no stars, no chemistry, no warmth of any kind from the very beginning. The warmth you are experiencing right now is not the normal condition of the universe. It is evidence that the universe is still running, that the initial order encoded at the Big Bang has not yet been fully spent, that the process of dissipation is still underway, that enough structure remains to sustain a star, an orbit, an atmosphere, and a biology capable of noticing. Every sunrise is not the default behavior of a cosmos that defaults to cold and dark. It is a scheduled event in the unwinding of an improbably ordered beginning, occurring on a timeline that will eventually end, driven by a starting condition that physics can describe but not yet explain. The warmth is not accidental. It is not permanent. It is the universe still in the process of becoming what it will eventually be: uniform, cold, silent, and unable to produce another moment of anything. Every morning the sun rises, that is not a given. It is a physical miracle running on schedule.